Uh, Hello, welcome to this tutorial session by IBM and IISc Fox, I guess. So it will be on semantic automation on data discovery, which will deal with uh, that semantic technology that enable automation for different data discovery tasks, for different tasks, for example, data enrichment, recommendation, data shopping. And so the speakers are Rajamohan, Ritvik, Balaji, Arvind and Sami from IBM Research and Anupam from ISC. So the first speaker of the tutorial is Balaji, I think. Yeah.
Right.
Thanks.
Okay. So hope you're able to hear me clear. All right. So I mean the abstract was a bit mouthful. So the main takeaway that we want you guys to take from this tutorial is data discovery. Of course, this term has been around for a while, so let's go over it a bit. So one of the recent things you might have come across is a data marketplace where you can monetize the data that you have, or within an organization if you want to find some data to train a model or to run some analytics, print some reports, whatever you want to do with data, you want to go and discover, find where the data resides in your own org, right? And you might also be familiar with some of the data sets because like you might have uh, like uh, I mean looking for them in Kaggle or any of the like data set search, Google data set search. So all of these are data marketplaces. So our kind of a motivation here is to enable uh, data discovery in these kind of marketplaces and use semantic technologies. I mean, of course, semantic again is a like a very old term. What we mean predominantly is using knowledge graphs and few other techniques that we will see. So there are three parts to this. I mean, as a caveat compared to the previous sessions, we will be focusing more on like sort of industrial research. So it will be like I mean, hopefully, like you will find it more intuitive, and of course, like please like feel free to stop us to ask any questions you have. Right. So we will kind of cover three things. I will kind of start off with search, and like Rajmohan will talk about enrichment, and later on we will have a session by Ritvik. So, so there are three things that I want to mainly talk about. Of course, like all of you are already familiar with this. What do we mean by search and exploration in the data marketplace? Search, it's probably like easy peasy for everyone. Very similar to a web search. You're looking for data sets or like any kind of data using keywords. You could also do more such things. We will see. You could like kind of instead of using a query, you could simply say that I have a table. Can I get a table similar to this? I have this data set. I mean that I'm using for some like say model training. I want to find similar data sets. That could be another way of looking at search, right? So that covers search. The other way in which people, I mean, of course, you might be familiar with this interface as well, which is like kind of a discovery or a kind of a browse mode, right? So you go to Netflix or any of these streaming platforms, content is recommended to you, right? So it kind of the home page is tailored for you. So we could think of your own organizations like data marketplace or any public, I mean all the government like kind of portals also to be tailored to you. That is the second portion where you browse for a data set. And the third one is like after you have reached a data set, right? So either using search queries or using browsing, you hit a kind of a data set. Now the third thing you can do is find similar data sets, right? So this is of course from the e-commerce world. If you like, if you buy or if you're on a particular item right now, then the kind of the engine recommends other similar products or things that are based on your profile, right? So that's the third portion. We can call this as recommendation. So we start with search, then we have sort of a browsing, then finally we have recommendations. So so this is a very interesting book. I mean, again, one of the takeaways from this tutorial, artist, this part of the tutorial would be this book, right? So this is the enterprise data catalog. The interesting thing about this book is it comes from the like sort of like library sciences world. So I mean, you kind of discover that a lot of things in the library sciences are applicable to the data catalogs too, right? So as you can see, things that we just discovered or just discussed right now, there is search, browse, there is something called complex search, which again is more similar to database queries, and then there is like glossary, right? So glossary, uh, typically it's kind of arranged, or like the ontologies and the taxonomies are provided to you by subject matter experts, but there can also be methods to automatically generate them. So if you have a glossary, then that's also part of this effort. Now let's start with browse, right? So I mean, this looks similar to Netflix or any of your streaming platforms, but how do you like kind of discover content in this, right? So, like immediately, what you see is like you find some, say, let's for example, instead of you clicking on some movie or clicking on some data set, you start with some category, right? So you start with, say, mortgage, for example, and then you go down and then find out that I'm looking for contact information in mortgage tables, or you're looking for more specific things, I'm looking for emergency phone numbers, or like 1-800 numbers. So what you're doing here is like kind of going down. We can think of this as vertically, like you are kind of refining your search query, and you are kind of trying to find more and more specific things that are of interest to you. That could be one way of browsing. Then the other one, which is more similar to graphs, is all these data sets are related to each other, right? So finding these relationships, that itself is a non-trivial task. Like lot of like kind of recent research is focused on that. We can call that as, say, semantic matching. So all these data assets or data sets are related to each other, either because they talk about the same kind of entities, or because you used some ontology in order to define what is a relationship, what are entities, what are relationships. So this is a second way where you go from one data set to another based on the relationships between the data. In the RDBMS world, this could be like foreign key relationships, but in the data assets or a semantic world, these are relationships that you will find in a knowledge graph, for example. Now, the third one is very industry specific. I'm not sure whether you all are familiar with lineage, like provenance and lineage. These are very enterprise terms. So, what this means is like if someone created a data set, you know that this person created it for this purpose. Maybe this came from some source. So, that kind of information is recorded. So, there is both design time lineage and runtime lineage. You store that, and later on, like if suddenly like I come and search for a data set and I'm interested in this data set, I want to know who else is using this, or which was the source. Like for example, can I train a model on this data? I mean, is there any restriction? Does it have personal data or any restrictions which prevents me from using this data for model training? So that kind of information, if you want to know, maybe you can go horizontally and find. I mean, kind of this is not too important. Like this kind of the book presents this as a horizontal traversal to find out where the data came from. Of course, the models once trained, they will also be part of this kind of a graph. You can find out that with this data set, these models were trained. So these are the three major ways in which you can browse. Now, before we move further, there are a few things in search, like which again you might be very familiar from the web search. Yeah, go
So
ahead.
I have just one question. So is it somehow related to active learning sort of thing?
You could make this as active learning, but usually the problem in these kind of spaces is there is very little, like say, repeat queries, right? So, I mean, usually these are long tail queries. A person is looking for a particular data set, and they might just use this once, right? So it kind of, that's the reason, that's one of the reasons why we are approaching this more from a semantic point of view rather than a machine learning per se, because like unlike say a web search, there are not too many users of these systems, and even when the users are available, they probably do these kind of queries like very infrequently, right? So you could learn quite a bit of things with active learning, but not per se that this query is related to this data set. I mean, that kind of learning, we may not have enough data, or we may not have enough users to kind of use that kind of approach.
It's okay.
All right, so this kind of again is really familiar, but I wanted to cover this like within search. I mean, you might be already using say and or quotation marks in web search. We can do all these things on the like kind of data catalogs as well. Now, this is a part like this is very closer to RDBMS, like where you are looking for something very specific, right? So, say I want contact information from this location, uh, like say of hospitals perhaps, or some kind of a very specific query. Then you will have to kind of frame a query like this. This is usually not that well supported in all the platforms, but this is something that one of the good things to have, right? Once you have a data marketplace and a search implemented on top of it, you might as well support these kind of complex queries. Now, let's see some examples. Actually, I'll just by examples I mean implementations of this kind of semantic search. So this is something that like this is from IBM. So like there is something called as Watson Knowledge Catalog. On top of which we have semantic search. So this is the example where like you know that you're looking for contact information or like on a mortgage related table. So one easier way this could be implemented is you have a sort of a business glossary where which tells you what is contact information. Contact information could be phone number, email address. So I mean, if somebody already tells you, like there are lots of ways to learn it, but if you already know that these are all the terms related to each other, you can simply use that in order to power your semantic search. Of course, you can bring all the machine learning in the ranking and all, but if you have a knowledge graph provided to you already, which says that contact information is phone number or email address, those kind of things, then you can incorporate it. That's one way. This is sort of related, but this is like kind of a more BERT or I mean what you might be like even more interested in this space. So what this means is the transformers that we train, they may not inherently understand relationships between entities. They do understand entities, they do understand relationships to some extent, but the reasoning is still like I mean not that well. So this is an example. The authors of this paper, this is a recent paper from May of 2022. What they have done here is they took a BERT model and then they made the model entity aware. What they mean by this is like there are few examples here. As you can see, the same example is repeated. Like say, give me all movies directed by Francis Ford Coppola. So that's the first query, and then you see the same query with their model, right? So where they have trained the model to know that Francis Ford Coppola is an entity. With this additional information, when they train the or when they evaluated the downstream task, which is like basically like bringing up passages in search, you can see a marginal improvement, right? So I mean, of course I'm saying marginal because it's not across the board, but there is an improvement. So in the first like the entity abstract, you can see that the Coppola example is not relevant, or rather like it's relevant in the sense that it's still a film director and a producer, but not necessarily the same person. In the second example that you see, Rumble Fish is an American 1983 drama directed by this particular director. So here, this is an example which a good example where infusing the entities into the transformers has helped this particular task. Yeah, this is an interesting paper and relatively new as well. Okay, so this is like going slightly deeper into what we can call as semantic search. I'm not sure whether how many of you remember Hotmail, which became the web version of Outlook, right? So, what is the relationship between Hotmail and Outlook? like unless like you're old enough like me, uh, or the model has been fed with a lot of news of the similar content, how can a model know Hotmail and Outlook are the same? Right? There is nothing closer to them in the like in the taxonomy as such, right? So it's not like email and electronic mail, or it's not like email and Outlook, or Outlook and Gmail. So here there is a historical perspective. At some point, Hotmail was called, Outlook was called Hotmail. So that relationship, if you want to know, this paper, actually it's not a paper yet, it's a blog post by Microsoft. They argue that this kind of relationships needs more special treatment than just the transformers, and then they came up with this model. I apologize for the color of this. What they have come up is like it's a unique architecture where they have like lots of entities, like I think like some 9 million entities, which they sort of use something like a one hot encoding, and then they convert it into like a 15-dimensional feature, and use this in order to rank. Like for example, for Hotmail, what is the closest entity? uh, Maybe Microsoft Outlook will be the closest one. So they show that this kind of a model performs better than a plain vanilla, like say a language model. So yeah, in the sense like of course the architecture portion, whether everything should be kind of every feature binary, that's sort of a more philosophical question. But this kind of a model helps with search. All right. So before I show more examples of like say the catalog itself, this is a nifty feature which we will see. Like tags are like long time back. There was a paper like again like lot of these things come back from history. Just like Hotmail may be familiar to you. There was at some point like we were using Flickr. I was at Yahoo at that point, and one of the things that we did was, how do you know what is there in an image? Right now you will quickly come up with a vision model where you can do all kinds of things. You can create the image, like telling what you want. But at some point we were using things like what people are tagging an image to understand what the image was. If somebody was saying that this is a cricket image, or like say Tendulkar, then you know that okay, maybe the image is about cricket or Tendulkar, right? So the paper was called folksonomy based approach. So basically you use people's tags in order to like learn things about the content. The same thing applies even now. The data set that you trained, you might give some tag to it, or you might just store it, the hashtags that you use. So this, of course, these tags have been around for a while, but they again have like kind of evolved to a lot of use cases in the data marketplace. So one thing which is sort of like tangential to this is access, right? So who can access the data set? So Google has the data catalog portion of Google, and also few other providers like Databricks. They use this tags approach to solve multiple use cases. One is access, right? If I'm searching for this, do I have access? Just like you tag a image or a data set with some user defined tag, you can also say that okay, who has access to it? What kind of a persona has access to it, that can be achieved using tags. So yeah, I'm just going to quickly show a few implementations of this. This Databricks as a catalog, they call it as a Unity catalog because they use this tag kind of approach for enabling access. So the Databricks, when you go to the landing page of Databricks, they have this arrangement, which of course looks very similar to Netflix. So how this, what kind of data sets are provided to you, and what happens if you click on one of these? This is similar to the kind of the initial browsing that we were discussing, like in the enterprise data catalog book. So all these things, like there is one example of the implementation. This is a slightly, you might be familiar with data.world. This is a slightly more knowledge graph oriented way of looking at data, where each data is connected to the other, like using say relationships in a knowledge graph. All right. So I mean, so far we have been talking about like data catalogs per se. So here, like this is like a data set engine, right? So this is like slightly, uh, I mean, we could. I mean, this is actually a DARPA project where we are trying to use web search in order to look for data. Of course, the data assets, the data which you typically see in a RDBMS is very different from say a web document. There are hardly any hyperlinks. There are like there is, I mean, there is a lot of redundant data, right? So how do you learn uh, kind of learn to rank data assets? That's a different problem in itself. But there are few things that are present in this which could be, this is kind of a like a template architecture for what you could do while implementing this kind of a search. So one of the important things, I mean, in this diagram is profiling, right? So that's probably one of the first things that people do. You kind of take the data, try to like kind of do a lot of things in the pre-processing step before you even use it for training or for indexing. It could be like things like finding the type, like curing the data, removing null values, from anything trivial to more complex, like finding out the bias, anything which is present in the data, trying to find out if you are allowed to use this data, privacy, incorporating privacy or access, those kind of things. All those things come under the profiling space. And then like there is of course a serving platform, a ranking and querying platform on top of all this. So this is like a really good paper if you want to build something from scratch. All right. So I mean, this kind of pretty much kind of summarizes what I was just saying. So there are two things which we are trying to work on in this space, especially in our team. One is like how do you learn representation of data, especially from tables, right? So I mean, a lot of these models that we know work well on text. Can we make those models also work on tabular data? How do you like kind of learn? That is one portion that we are looking into. The other one is like what can we do at the column level? Like for example, if I have a data set, I want to find a column which can be added to this table, right? So like for example, I have say you will probably see this example later on. Like I have height and weight. Uh, like I want to predict say say the like heart attack of a person or something. So if you find that in order to do this prediction, you need some other column which is available in the overall catalog, how do you find that column and add to this table? That could be one open problem. It could be like not just one column, like several columns. You want to merge tables or find whether two tables can be joined. And those are some of the things that we are looking into. Okay. So the one that I showed is more of a the Octus paper is like more like academic, or say we can say that it's more relatively smaller data sets. If you want to do this at a much higher scale, then there is this paper which of course like a slightly older one, which is the Google dataset search, right? So again, lot of things here in the Google dataset search. I mean, of course, the paper talks more about the architecture, but there are few things uh, a public dataset has which the internal datasets may not have. This paper kind of exploits the metadata in order to like figure out what the data is. So in general, this is a kind of an open problem. Like, do you learn from the data or just from the metadata? So this is kind of a takes a like metadata heavy kind of approach. All right, so Okay, let's see. I'm at the top of the hour, so if you guys have any questions, I can take now, or otherwise I will ask Rajmohan to present, which is like kind of follow. I mean, just we just discussed about this octets. Uh, the next session will focus a bit more on this aspect, which is on the enrichment.
Thanks, Balaji. Can you hear me, Balaji and others?
All right, sure.
Hello.
Rajmohan, can you hear
Yes.
us?
Yes, I can hear you, Balaji.
All right, cool.
Okay, let me share my screen. All right. So let me know if once my screen is visible to everyone. Hello. Is my screen visible, Balaji?
Not yet.
Okay. Just give me a minute. It is asking for some permission in my MacBook to be enabled for screen sharing alone.
Raj, just go to the screen recording permissions and add Chrome or whichever browser you have there in the system setting, Apple system setting. Search for screen recording,
Yeah, yeah, yeah.
and in
Yes.
that add Chrome or whichever browser you are using, and then but you have to restart the browser after that.
Yeah. Hello, everyone. Can you see my screen now?
Yes, yes,
Okay, cool. Sorry about that. So I
no
think
problem.
Admin should probably add this screen sharing also along with camera and audio check at the beginning of
No,
joining
no problem. It's okay.
them. Okay, so let's get started. First of all, good afternoon to everyone. My name is Rajmohan. I work as an advisory research engineer at IBM Research. Today, in this tutorial on semantic automation for data discovery, I will be covering a specific topic. This is about data enrichment with a focus on data discovery. So let's get started. So as you know, right, we are in the setting of a data marketplace. In sometimes I'm going to call it in more generically as a data catalog. So in this setting, we have data sets coming from diverse sources, right? And this data is going to be in different formats. Typically, the number of data sets as well as the size of these data sets individually is going to be very huge, right? So this is the setting that we are operating on. And in this setting, we may not have any metadata associated with the data sets, which is the general case. And even if we have some metadata associated with it, they may not be in any standard format in most of the cases. Now, with all these constraints, how easy it is to consume a data set, right? So the data may not be easily consumable, first of all, and also it may not be easy to discover the data set itself. Having said that, the goal of data enrichment here is how do you make these data sets discoverable and readily available for consumption by the data consumer. So that is what data enrichment is all about. Now we are going to look at data enrichment from 5 different angles, right? So that is what I have put out here on the right. The first one is on data quality. When we say data quality, nobody wants to discover and consume a data set which is of low quality, right? So we will talk about the importance of data quality for improving the discoverability as well as consumption of a data set. Then we will get into the metadata part. How can you utilize the available metadata? How can you infer additional metadata, enrich the metadata, and how it can help for data discovery ultimately. And then we will get into the relationships part. As you know, data sets are seldom used as alone. Generally, you relate a data set with other data sets, and that's how you consume it. So we will look at data relationships and how it helps in this particular problem setting. Was there a question? No. Okay.
No. Yeah.
Fine. So then we will get into the knowledge representation part. So how can you represent data in the form of knowledge graphs and ontologies and how it helps in data enrichment for data discovery. Then finally, we will talk about data lineage and governance because trust and transparency is very important when you want to consume a data set. So at the end of this talk, we will touch a little bit upon data lineage and governance as well. So this is the outline of my talk today. So let's start with data quality. Right. So data quality, as we all know, in simple terms, it is about whether a particular data set is good enough for a particular use case or a scenario, right? And you can measure data, and you can measure data quality along different dimensions, some of which are like how accurate the data set is, whether the data set is complete, whether it is consistent, whether it is a reliable data set, and whether it is up to date. These are all different dimensions you can measure a data quality. Then comes the data cleaning part. Now you identified some issues, let us say, with respect to data quality. How you are going to fix these errors, for example, missing values and other errors, in order to produce a reliable analysis using the data set. That is the data cleaning part. Now, this data quality and cleaning have been looked at exhaustively, as we all know in the research community previously. So I am not going to talk about individual approaches of data quality and cleaning and bore you all, right? But the key takeaway I want to talk about here is that if we look at it from the data marketplace and data catalog point of view, the main challenge comes from the fact that here we have diverse data formats and the scale of the data is going to be huge and varying. In this kind of a scenario, what additional things we can use to make the data quality analysis and management journey fruitful, right? So I will talk about a couple of things here. But before that, the motivation is as you all know, when you improve the quality of data, it's going to help the data discovery ultimately. Hence, ensuring adequate data quality is a very important task, right? Now, let's look at it from two angles, right? One is about the collective part, and the other one is about the semantic part. First, let's look at the collective part. Now, how can you use the collective wisdom of a data marketplace or a catalog to help in your data quality, right? For example, you can auto generate your data quality rules from existing data in your data catalog and customize it then based on your needs. So these rules can then be validated on the new incoming data, and you can flag the violations, right? This is one way that people have looked at utilizing the collective wisdom of a data catalog or a marketplace. Now I am giving another concrete example. This is a research work where they have built some kind of a RDF data store on top of data lake data, for example. Okay, so this is about some diverse data sets coming in from different sources. Now from this they built an RDF store. It's some kind of a graph representation of triples, and using this, what they try to achieve is, can we do better integrity constraints discovery, and can we identify data errors and suggest repairs in a better way, right? That's what they tried to do. For example, here I have given a small example from the paper where they kind of taken two different data sets which talk about the same location, but when you look at their latitude longitude, they are not matching actually. So this is something they inferred via the constraints learned from the collective wisdom, and they kind of then flag this error and suggest data repairs, right? This is some work around utilizing collective wisdom and knowledge from all the data sitting in your catalogs, and how you can use it to improve some process. For example, here, how do you discover integrity constraints, and how do you identify errors and suggest repairs? This is one way to do it. The other one is about the semantic part, right? So this is something that many of you might be familiar, right? So in terms of semantics, there's a lot of work on the representation learning, even with respect to tables, and how table representation learning can help in many data tasks. Like for example, can you detect errors in your data set, or fix errors in your table cells, or cell filling can you do in a given table using representations learned on the tabular data, right? These are all different kind of data cleaning and preparation tasks. Now, can we utilize collective wisdom of data catalogs also by bringing in additional metadata and relationships into this representation learning setting? That is also something interesting. A lot of research is happening there. So these are the two different things, collective and semantic part, that there is still scope for a lot of problems with respect to a data catalog setting. Now we are jumping into the next one, which is about metadata enrichment, right? Till now we have been talking about data and the quality of data, but metadata also plays a very key role in terms of data discovery, right? Now the problem is, generally data sets contain very limited metadata, and this metadata can be of different types. Some metadata could be of describing the data set, something could be constraints, annotations on the data set, or it could be about access protocols. There could also be some business metadata, like for example data classification, tags, business terms, PIA details, and this metadata could be manually added, or it could be something that are inferred by some programming techniques, right? These are the metadata available with you, and this metadata provides a lot of business context, and they are very useful, which is very evident, right, for data discovery as well as semantically understanding what each data set is about, right? But the major problem is, this metadata is generally not available in many data sets, and they may not be in a standard format, and they are all locked in silos within each application generating the data set, or the personas generating the data set, without any standardization. Now, there are some open standards available for dataset metadata, like for example, schema.org, W3C. These are some familiar standards many of you might be aware, which are trying to standardize this metadata. But the problem is, when you start to work on this problem, whether you want to follow a non-proprietary standard like schema.org or W3C, or you want to use any custom proprietary standard specific to your own team or an organization. That is one problem. The other problem is the amount of effort needed, right, from the dataset owners to create this metadata such that it conforms to the standard, and maintaining this metadata are some of the constraints why this is still not a norm across the data owners. Now, for example, this is one example I am flashing from the Google's dataset search engine paper, right? So if you look at the date column, right? For example, I mean date property. Each dataset has some kind of a date property because it's a very preliminary data, right? It could be about when the dataset was created, when it was modified, or any other date column. But the problem is, even though the standard requires it in some particular format, different data sets have it in different formats. Notwithstanding that, there are data sets which just mention it like this is published in November 2018, something in a natural language. And even some data sets have it in different languages in natural language just to convey the date, right? And also these metadata are sometimes generated programmatically. Now in such cases, what happens is a problem happening in one data set will then be replicated across thousands of data sets that are generated via the same program or similar programs, right? So hence, understanding the meaning of existing metadata and how do you perform an inference on this metadata and how can you enrich this metadata, right? These are some really very critical as well as challenging tasks. Google Dataset Search try to address few of the problems, but these are very specific to web datasets and pertaining to specific standards like schema.org. For example, they try to come up with some operations to normalize and clean the metadata for web datasets adhering to the schema.org standards. They also try to reconcile information mentioned in the metadata fields by using some knowledge graphs. They use it to reconcile and then clean the metadata before accepting the final version of a metadata for a given data set, right? But as I said before, right, there is scope for a lot of research here considering the enterprise scale data sets, limited metadata available with the data sets, and the quality of metadata, as we have seen in some of the examples, coming in from different sources and different personas, right? This throws in a lot of challenges in addressing the metadata enrichment problem. Now we spoke about data quality and metadata enrichment. Another important aspect is about data relationships, right? As I said before, data sets are seldom used in isolation. These relationships provide a lot of context to understand the data. Now, the datasets can be related in many ways. Traditionally, datasets are related in terms of join and union relationships. And these relationships discovered, as you know, is going to help in our downstream search and exploration, which is what we are interested in ultimately. Now, several methods have been proposed for data relationships. Again, we are not going into the details, but I'm going to touch upon the high level approaches, right? For table relatedness, joinable tables, unionable tables, a lot of research has happened. For example, let's say we want to find joinable tables. We will start with a table and we want to look for other tables that can be joined with the given table. This can also be put in another way, which is a more relevant problem for a data catalog setting where we are given a data table. Then we want to find out and recommend some additional features or new features for the given data table. Again, this is some variant of the problem, the traditional problem. Now, an example I have given here from one of the recent papers, where on the right, on the left, you have a table with the 3 columns, company name, and some funding and grants details. This is, let's say, the original table. Now, after enriching, you got the table on the right, where you brought in some additional column data from some other tables available in your data catalog, which has kind of enriched this data table by providing additional context, right? So we probably brought in one additional column here about the total contribution, right? So this is just one toy example to convey the point about how, given a data table, the problem of recommending additional features will look like. Now, early approaches here, they have looked at set similarity based algorithms and they will find exact results, but the problem is they are not scalable. Then there have been a flurry of approaches which are approximation based approaches, and these are mostly variants of LSH, locality sensitive variants, right? This early approaches mainly focused on equijoins, but there has also been a lot of recent approaches which have been working on semantic joins, where you have similar meaning words and sentences across tables that you learn embedding and then try to kind of correlate them across tables, right? This will make sure that you don't miss out on identifying and handling misspellings and discrepancy in the format and
Hello.
technology.
Uh,
Yes.
I have just a question.
Yeah.
So nowadays, modern embedding techniques can encode many information in single compact vectors. Okay, so why is it the case that I have to look for the semantic things separately, semantic relationship separately? I just encode everything, by possibly by using early interaction model, let's say, okay, and then use LSH once you get every vector, and then you just apply LSH.
That is right. So that is something where research is happening right now, right? So that is not shown really that it will outperform traditional approaches yet, right? So for example, you do some kind of a representation learning on the tables and use that for table search or table similarity. You could do that. There have been a lot of recent work happening there, but still there is, it's nothing like that is the state of the art that it has solved the problem of relationships discovery in such a large scale, right?
Hmm. Okay.
That is my point of view, right? That there's a lot of research happening in what you are saying, right?
Okay.
Right, even I have one point here, right? So if you see recently there's a lot of explosion about these large language models and embeddings generated via these language models. There has been some deep learning based approaches where they do learn these embeddings via these large language models and then use it for this kind of traditional tasks, for example table search, table similarity, etc. They have been shown they have been showing promising results, I would say. Now, a little bit on the union problem, right? So here it's a little bit more harder than the join problem, because here tables may be unionable on all the attributes, or it could be that they are only unionable on a subset of attributes. So you need more principled way to first identify which are those attributes that are unionable, and then those tables that can be unioned, right? And how do you evaluate it? So just a motivating example to convey the point. You here we have a couple of tables again from the same paper, right? Probably. So these are two tables talking about gas emissions, but they are two different tables. One is about the London location, one is for the Washington state, and there is some kind of similarity as well as they are different in some way, but they both are talking about gas emission related data, right? So again, here also a lot of work on the overlap and similarity functions, traditional approaches, and also there's been a lot of work on mapping this data into some external ontology and then try to solve it. This is also again a lot of work still happening here, also utilizing the representation learning based approaches as well recently. Right. So just one other work I wanted to show here. Like till now we have been talking about these relationships. So these relationships could also be at the conceptual level, and it could also be tied to some downstream task. So there's also a lot of work recently wherein you want to enrich the table but tie it to some downstream task. For example, I will give you a motivating example from one of the recent papers. So you have some table here which is containing details of a product, basically product name and category. Now this is your table and you want to do an ML task of predicting the sales, right? Now given this task and you also have your data catalog or a lake, right, with you. Now can you enrich this table with given the particular task also? That is the ask here. And here what they were able to produce is something like this, where they were able to bring in additional features which would be useful to predict the sales here, right? So here you have this original two columns. Additionally, they have this enriched columns. description and publisher, which have been produced by the system, right? And this is supposed to improve the accuracy of your machine learning predictive models built with it for the given task, right? And as you can see here, this kind of task requires both row and column alignment, and they are really complex tasks, right? But there's been a lot of work happening here as well, right? So this is where I will stop about data relationships. I will go into the next dimension, which is about knowledge representation, right? In knowledge representation, what I want to talk about is how we can understand the underlying data by utilizing the external knowledge bases and knowledge graphs, right? It could be an ontology or a knowledge graph. For example, given a table, can we link the table columns to some, say, standard Wikidata concepts? These kind of problems, right? So there's a lot of cross-domain cages as well as domain specific ontologies we have, right? We can utilize them to enrich your given structured data sitting in your data catalog or a marketplace. For many AI applications, what it requires is you have to analyze the correspondence between your structured data and the entities which are in your cross domain knowledge graphs or domain specific cages and ontologies, right? There are many cross domain large cages, you all aware of it, like dbpedia, wikipedia, wikidata, sorry, and yago, etc., right? So the thing is, these are targeting coverage. When we say that it's containing details, but that will be limited if you take a particular specific domain. That's why there is a need to have domain specific ontologies as well. There's a lot of them for different domains, and these ontologies provide you fine grained information with which you will be able to understand complex relationships of the entities within that domain and deep hierarchical relationships, etc. So these are the things available. Now we can use them to encapsulate a semantic knowledge, right, from these ontologies into our structured data set, and that way we will be able to provide a better understanding of the data and provide better reasoning about the data, right? And this enables a lot of reasoning capabilities, as we have been talking about. In the interest of time, I'm going to rush a little bit. There's been again some efforts around building a semantic layer on top of a data catalog itself, right, by using this knowledge graph. I'll talk about one specific work here, right, which is in this particular setting, KGLAC. This is some work where what they try to do is they try to build some kind of a knowledge graph on top of a data catalog. The first class citizens here are your tables and columns and files. Let me flash an example from the paper itself. So you can see here what they are trying to do is you have this data set table and column from your data lake or a catalog. Now these are your entities in your table. Along with it, there are also many other relationships that are discovered or inferred. For example, it could be that there is a total compensation and total pay, they are semantically similar, or there could be a job title and title, they are content wise similar, or it could be a basic relationship that something is a part of something else. All this, so many kind of relationships manually added as well as inferred, right? So once you have this kind of a knowledge graph on top of your data catalog, what they try to show is it enables various functionalities, right? For example, once you have some kind of an ontology for these relationships and entities similar to what we have seen in the example, and they have some kind of a representation learned for the columns in order to identify these relationships, semantic relationships across columns, then we can consider it like a deductive graph, utilize it to infer many other interesting relationships, right, on top of this particular graph. And you can also have a data discovery operation itself run on top of this graph to do your table discovery as well as to identify which tables could be unionable or joinable. You can basically build some kind of an interface on top of it and try to make it an interactive process for a data consumer to compile a data set on the fly for a given task, assuming that such a powerful knowledge graph can be built on top of a data catalog, even though what we have seen is some kind of a toy example here, right? So this is about knowledge representation. Again, as we discussed, right, this is again a very challenging and interesting problem. A lot of research is happening. Now that was about knowledge representation. I'm going to cover data lineage very quickly as the last dimension that I want to talk about. right? So data lineage, as Balaji has already alluded to, right? So this is something that is very critical from a business point of view, right? You want to trace your data across the system. Like for example, it goes across your pipelines and dashboards. You want to trace it end to end, right? That is what we call it as data lineage. And as the name suggests, right, it is going to bring a lot of trust and transparency to data consumers about data sets. So what are those questions that a data lineage system can answer? These are the questions, like for example, where the data set came from, what are the ownership details, from which data sets it was derived, what are those use cases where this particular data set has been used before, or were there any issues identified before. So these are all the data that can be part of a data lineage or a data provenance system, and it will be very very useful for improving the discoverability as well as improving the consumption of a data set in a data catalog setting. Again, there's a lot of work on how you can do some of these tasks in an automated manner. How do you do automated data lineage tracking in some of these select scenarios? In some scenarios, it is still a manual effort, and it could be hybrid as well. So you have some kind of an automated tracking enable, and then there is a manual process where you kind of annotate on top of it with the additional user knowledge, which is more of a workable solution for difficult scenarios, right? Now, when we say data governance, basically what we mean here is that in an enterprise setting, there's going to be different kind of personas, and the experience needs to be different for each persona. For example, in terms of what data sets you are going to show to him, and how, in what curated state, and what are those metadata which are customized to the user's needs. These are all the different kind of customizations to be done for each persona, and these are going to be defined by different policies, right? So this entire thing is what we are calling as data governance here, which also plays a very key role in providing a customized view and a customized experience for a data consumer. I think I will stop here in the interest of time, right? So these are some of the references for the talk, and I will take any questions if you have right now, or I will pass it on to the next speaker. Thank you.
Any questions? There's some questions on. Okay. Any questions? So I have one, sort of last questions here. So to both of you, perhaps. So when you do discovery, you mean like some sort of discovery from the existing set of data. So did you find any use of generative model in this context? Like, for example, suppose you give some data and uh, the generative model sort of predicts what you want to search in some sense, okay, and then it searches for that point that is giving output by generative model.
So actually, yeah, I mean, after that will be like sort of the final solution where the model gives the answer you're looking for. But so far, like where we have found generative models used is more in the data generation part. There is this paper called KELM, which kind of sorry. So the KLM paper tries to convert triples from a knowledge graph into natural language sentences, and then uses it to augment the C4 training data to train T5. Right. So that's one use case we have seen. And it's a very good paper. That data set is also available. It's called KELM. So that's one place where the model is trained for predicting the mask prediction task, which could of course be used downstream. So what we did in a somewhat similar setting is um, we took a similar approach where we infused knowledge graph entities into a language model, but our downstream task was to generate entities rather than any text. So like if you start with say like the person's name, like you want to predict, I mean, we don't want the name to be like sort of biased, like a white Caucasian name, right? We want more diversity. I mean, assuming that's our use case. So we kind of trained a model with some hard constraints to predict entities which are more diverse. besides other sort of constraints. And we kind of this paper was accepted at a workshop at ICLR. We called it as the fair data generation with hard constraints. So these are two things that we are familiar with. But of course, like what you're saying, pretty much like if you could have a chat GPT which could simply answer, that would be ideal. But
No,
we
not
haven't.
that what I mean. I'm saying is that if the answer is hard, then it will be given, that will be hinted by some kind of model in between.
Yeah, makes sense.
So this,
Yeah,
and this model can be like, some kind of personalized, in the sense that uh, if your model accuracy is low, it's acting as a hint provider. Let's say to be very simple, simple things, like you input something. Sorry. So you have a small data set, okay, from your regime, and you have a service model, okay. You give the input to the service model, get something out of the service model, feed it into the training model, get the output that this person wants.
yeah, it definitely sounds interesting, right? So
Hmm.
I mean, definitely it could go. It could be probably also used to generate good prompts,
Uh-huh.
right? Yeah,
That's what I'm saying. Why
yeah,
more like a hint rather.
correct.
Yeah.
Yeah, yeah. Actually, we ourselves haven't tried, but we will definitely
Okay.
share papers if we find related
Sure.
to it.
Sure. Sure. Okay. Thanks. Okay. So yeah. So Raj, you can
Thanks everyone. Yeah.
read quick. Oh.
Hi, can you hear me?
Hello. So, in general, when we construct any semantic network, so we find the abstract meaning of the words, and this abstract meaning would come from any existing knowledge bases like DBpedia or Wikipedia. So, how far like this database is updated for the recent English terms. So, when we find some data set that contains recent data, and do we find the meaning of those informations in the existing database knowledge bases? So if in that case, whether using the traditional semantic models are better than word embedding models, like he said.
A related problem is like the enterprise jargon, right? So I mean, as far as the English language or the new words themselves are concerned, I would think that's a relatively solved problem because people are using crawl data, Wikipedia. I'm sure all the pen and other latest sources that they have. I mean, obviously, like I mean, if you look at the Bloom model, maybe you could figure out like which ones are actually being used. But the other problem in the enterprise where the industry jargon is not known to the language model, that's a much bigger problem, right? So if you use these web trained models on your enterprise catalog, then you definitely need to infuse. So the paper that I mentioned, the KELM work, or there are a few other works, even in the my presentation, there was this entity aware transformer. So those are approaches where you need to bring in your own like taxonomy and infuse it into the language model. So yeah, I mean, how often it's updated, that probably will be dictated by the each company which wants to do it. But on the web scale, I'm not sure exactly what is the answer, but I would think the latest words are obviously included.
Okay, sir. So, in general, like if we take any word embedding models, the context is determined based on the words already present in that
Right.
document. So,
So I mean, although all the words are not present during training time, it's not as if an unseen word cannot be like embedded at all. I mean, a similar word or using stemming, or we could simply like use like I mean, continuous learning approaches to kind of just ask the user, what did you mean by this? So I mean, it will be quite rare to find words which are like not at all there in the language model training. Even if that is the case, we could you just ask the user what was the meaning for this.
okay, thank you.
Yeah. So maybe Ritik, you now can start.
Yeah, sure. So can you hear me?
Not much, no. So it's not the
Okay.
voice is not clear.
Now can you hear me?
Yes, yes, much clear. Yeah, please go ahead.
Okay, all right. So let me try to share my screen. Yeah, let me know if the screen is up. Okay, sure. Um, so right. So far, basically, so my I'm Ritvik Chaudhary. So basically, so far you have seen this data discovery and kind of data enrichment that are like the properties of the data that that you expect to be there or that you want to enrich it with. But now the next question that becomes important is basically how do you do this within the data exploration, and that's something that I'm going to talk about in this particular tutorial. So examples of within data exploration, it seems pretty simple from the outset of it, because it's an we just want to learn more about the data set once we are given whichever that we are given with. So here is a toy example which actually includes just a table that you can see where there are individuals' ages there, gender, residing city, monthly house rent, and monthly expenditure is given. So for the traditional tools actually, and also I mean in general, it is pretty easy to find some of the central tendency based measures based on given a table, right? Even going within the categories, one can actually find out different easier measures. But then there are some of the aspects of a table which are more interesting, and we might want to know about that more rather than just want to see what are the central tendencies of this particular table. So for example, here for individuals older than or equal to the age 32, average monthly house rent in Bangalore is 27,000. So that's kind of an information that we want to carry forward with, because that is something that has a really different kind of a pattern as compared to the overall monthly house rent if we look at the other category, that is the age less than 32. Average rent in Bangalore is significantly more than that of Kolkata. So basically, that's another information that is there. And average monthly expenditure for individuals older than or equal to 42 residing in Bangalore is significantly more than the rest. So these are the kind of insights that are rather more impactful as compared to just looking at some of the central tendencies or just the variance dispersion, this kind of things. So that's actually that's where it creates this notion of interestingness of data cubes. And I'm going to talk about this. This is a vastly researched topic these days, that how do you actually automate this exploratory data analysis so that a person who may not be that knowledgeable about the data, or what are the approaches that one should go for, they can still do the data exploration with the help of the system rather prompting them what they should do, right? So usually within data exploration is the beginning of gathering initial insights about the data.
Ritvik,
And yeah,
can you please click that hide button? Yeah, just click on hide. Yeah,
okay, sure.
yeah, thanks.
Thanks. Subsequently, yeah. So usually within data exploration is the beginning of the data analysis, which involves gathering initial insights about the data and subsequently deciding on what are the subsequent analysis to be done. And one can actually run into very wrong path if they do some wrong data analysis at the initial stage and may not get to the insight that they want to gather as quickly as possible. So it is important to be right and to be on the to be helping the user in the right direction for coming up with the insights in the overall in the overall process. So now data exploration can be performed by technical and also non-technical users. However, based on the roles, responsibilities, intent of the user, different users might be seeking for different types of insights. So for example, in a financial data involving housing loan amount taken by customers, a data scientist might be interested in many of the different things. One of the questions that he might be having, that how likely that a customer will actually not default at the end, right? Whereas if there is a lending manager, he might be interested in that what is the upper bound of the loan amount to be given to a customer based on the different attributes of the customer. So basically the intent of the user becomes important as we do data exploration. So it's not that, I mean, same data exploration can be actually given to all the users at the can be shown to the all the same users, because that might not be interesting for all of them. Generating non-trivial data insights automatically is a challenging task. A few existing tools that generate some insights given a data set are obviously Tableau, Microsoft Power BI, IBM Cognos is there as well, and ChatGPT to a certain degree. But however, still, when we want to really come up with like data cubes which are interesting, there still are gaps which there are more of researches going on in that direction. So essentially, I'm going to talk about a few of these research directions, mostly covering these three papers. So one is on the CDB, which is basically more towards the visualization, that given a visualization of how do you visualize a chart from using through data exploration, and what are the recommended charts that you can look at. And then obviously there is a deep reinforcement learning framework for exploratory data analysis, where actually, if the user really doesn't know what he needs, can the system actually slowly move him to a direction where actually most of the people have done previously, and so that the person can actually get to the insight that he's searching for. And then one of the more important question is what is interesting. So predicting what is interesting by mining interactive data analysis session log. So basically these are the three papers that I'll be talking about a little bit. Now CDB, this is a motivating example I'm going to go over. So this is about the showing the visual representation of data. So the following illustration has been taken from CDB, this particular paper. The illustration is a journalist is doing research on the age of getting married among the millennials. And from the previous analysis, it has been found that the average age of marriage has gone up among the millennials. Hence, it raises a few questions about how marital status affects the socio-economic indicators like education and income. And journalist is using some US Census data for this. Okay. Now, if she really performs this analysis using the tools that exist, there are graphical tools that exist. Excel provides graphical representations pretty well, and there are other tools that are there as well. So one can use that to perform the analysis and can have several visualizations on the data, such as income against marital status, then education against marital status, and also one can look at the impact of the marital status and the hours worked per week. How does that actually come about? That, however, at every step, whenever they do the analysis, there are exponential number of options open up, because they can go in a certain direction to do further analysis in that direction, but without knowing whether that will lead to a really good insight or not at the end, right? But however, what these authors claim that, and in general it is true, that if there is it has been found that the comparison between a target data, for example, this unmarried adults, against the reference data, which is the married adults, are actually usually interesting. So basically, you essentially want to do a comparison between two classes under different attributes, and want to see what are the cases these are like giving rise to different kind of distributions. So for example, here, if you look at this two categories, unmarried adults and the married adults, and there are two subcategories that are based on the gender, that female and male. So what has been observed is that average capital gain is pretty much the same for unmarried females and unmarried males. There is not much of a difference. But surprisingly, for married males, the average capital gain is almost twice that of married females. So then that's actually right there an insight that is more impactful, which would not have been obtained if someone would have looked at all of this in silo. This bar charts in silo. So basically, that's why this kind of comparisons, comparative plots are important, and that can give rise to more important, interesting insights. For example, similarly, if we look at the average age for that particular data, there is not much of a distributional difference between the group unmarried male and females, and also married males and females. So that is not an interesting insight, but rather this figure 1 is an interesting insight. So as I mentioned, in figure 1, although the distribution of capital gain among unmarried male females are almost the same, but for married females, the capital gain is almost half of the female or half of the males, which give rise to disparate distribution when compared to the same against married adults within the unmarried male split over gender. So CDB actually is based on this kind of analysis. They will always form a target data, and then they will have a reference data, and then try to come up with interesting measures and recommend charts based on that. So usually this efficient data-driven visualization recommend support visual analytics in CDB. It is based on a client and the server that is there. And in the front end, they have this client where actually the user can select a data set on which they want to do the analysis. For example, expenditure data that I just showed there. And there are query selector that they can go for. They can select the attribute to be city, and they can put the value to be Bangalore. And the contrasting class here would be that is the not Bangalore, which is basically the city Kolkata in this case. And there is a visualization builder that's as well. So basically they want to have gender on the x-axis and the monthly expenditure on the y-axis, and there is an aggregator they use that is the average. And if they look at this, then basically this is what they find. This is the visualization pane that actually shows this particular plot. But along with it, they come up with a recommendation. So in a way, I mean, the recommendation is similar to that to what they have chosen. It was based on the monthly average monthly expenditure, but the recommendation is saying that you can also look at the plot, which is basically average monthly house rent based on that. The question is, I mean, still here, I mean, how this recommendation is coming up, how CDB actually proposes the recommendations, I'll be talking about. But at the same time, it still needs a pointer from the user to start with. That user has to give this kind of inputs to make the system understand that what is the first initial plots that it must show to the user, and then point to the recommendations around that. Okay. So just get into a little bit of technical depth of this. CDB is essentially a middleware which can run on top of the SQL compliant database systems. And the architecture of CDB is provided below. So basically, obviously, there is a client and there is a server and there is a user. So user actually provides this selection criteria. And based on that, there is a query gets built. And then based on that, obviously, it fetches the data from the database systems, and basically it generates the view for that. But then there is an execution engine that is also there, where there are two things that happens. One is sharing, the other one is pruning. I'll be briefly talking about that in short, which are kind of an optimization techniques that they use to get to the recommended chart that they might want to show to the user, which the user might be interested in. And obviously, based on the recommended chart, then the user might actually choose that recommended chart and see that recommended chart and subsequently get some more recommendations. And in this way, actually, you can think of that it's going towards a tree structure. It gives rise to a tree structure for the analysis. Now, obviously, I mean, as I mentioned, it needs an initial pointer from the user to start with. Now, the question is, what happens in this execution engine? Because there could be many plots that could be important, or that one can come up with. But how does the system actually decide on which of the plots that it might want to show, right? So, why is optimization needed at all in this? So for each aggregated view that CDB actually generates, for each aggregated view, CDB actually generates a SQL query corresponding to the target and the reference view. Target is the target class, and the reference class is the complementary of the target class. And essentially passes on these two queries to DBMS. Essentially, it repeats the process for each aggregated view. It can calculate average, it can calculate mean, it can calculate standard deviation, whatever that it wants to do. It essentially then computes a distance between the target and the reference view distribution, and finally returns the k views with the highest utility. So basically, it essentially, computes how disparate the distributions are between the target and the reference class, and one can do it through full vector live distance or any of the things that they want. But however, what ends up happening is basically they do a lot of comparison, because just imagine there are a dimensions and there are m possible measures to compute the distance, and there are f aggregation functions. Then obviously they have to send this twice a times f time f time m queries to actually come up with the final view. So naturally they need to do some optimization, because more often than not they do not need to actually do the computation for each of the queries, because many of them will be overlapping at the end. So they do computations efficiently. If they can do that, then perhaps they can actually reduce the number of computations that they have to do. So that's where this optimization part comes in, where there is a portion called sharing. So for a particular user input, usually the queries that are evaluated are very similar and only differs on the attribute used for grouping and aggregation. So for the group by operators, there are many times they are going to use one of the attribute, they group by that, and actually they do the computation. So for all the queries which are grouped by the same attribute, they actually just do not need to scan the data every single time. They will rather do it one time and get to the result. And there could be several group by operations, several group by attributes. Let's say there are m of them. Then obviously there are at most this product of cardinality of each of the groups that have how many however so many categories that they have. But these are the maximum number of groups that can get formed, and then optimization can be done to optimally group this attribute to get to a particular answer, particular view that they particular computation, and then find out how one reference view, its target view, is different from the reference view, how the distributional change is there. But obviously, most of them are not going to work, because the thing is that even if they manage to do all this computation,
Hello, can you hear me?
they're yeah, is there a question?
Yes. So just have 2 to 3 minutes, so that we can have 5 minutes for questions.
Oh, okay. Then I will move quickly. So anyways, so basically there is an optimization technique. There's a pruning technique that also happens. So basically, here what they do is they just decide on what kind of views that they want to show, based on some confidence that they have that how these views will be, how the target view and the reference view distribution will be different, and they actually do it using just pulling a sample from the data, pulling some from different spaces of the data, and do the computation and then decide. Then there is this other method. So CDB actually needs the user input, but then there is this method that is on deep reinforcement learning framework for exploratory data analysis, where actually there is no user input is taken at the beginning. Rather, the user just inputs the data, and the system tries to guide the user to a certain data discovery kind of direction. And what happens is that in the deep reinforcement learning paper, let me just show you the architecture that they use. Actually, there is an environment, and the states are the displays that comes after one has taken an action. By action, what I mean is you can do group by, you can do filter, one can do one can also go back to the previous display. Those are the possible actions that one can take, and every state is basically nothing but the display that they get after taking the action. And based on the display that they get, they actually convert it to some kind of a numerical measure to get to an understanding that how this display can be actually how good this display is. And based on the display, and they actually assign a reward for that particular action that has been taken in the previous state, just like what happens in the reinforcement learning. And then the system actually decides what should be the next action. And then based on that action, basically it takes it to a new state of the system, which is basically a new display of the table. So one of the action is basically this filter, that is city is Bangalore. Through that, one can perform these are the kind of actions. And the deep learning procedure actually has this as I explained, there are states are represented by the displays. I mean, basically, whatever the display of the table, whatever the view of the table that you have after taking an action. Action is a tuple essentially, which is basically filter, group, and back. Back is meaning that, let's say, I mean, you reach this situation, reach a particular view which is not giving rise to any of the interesting views, then you can go back to the previous view and then do the analysis from there. Filter is just filtering by one of the values, and group by is grouping by one of the attribute and applying an aggregated function on the other. So essentially, I mean, this action space is defined by this a comma x, where a is this set of possible action, filter, group, and back, and this x is the corresponding parameter on that action, that is basically on what attribute you are actually going to do the group by, or on what attribute you are going to do the filtering. And similarly, there is a reward at the end. The reward is more dependent on the interestingness, diversity, and coherency of the table. So basically, there are some interesting measures that exist. I mean, here they are looking at the skew distribution. So basically, overall, whenever there is a pattern which is different from the overall data set, that's called the interesting part. And there is this diversity which is there also, that leads to that how diverse the data set you are looking at for every single trial. And there is a coherency part, that is basically how close the action is to the human action that is given by the system. So through that, I mean, basically they take a weighted measure of all this rewards and all these scores, and basically give a reward to the system, and through that process the system actually learns. So I'm not going to talk about how the system actually learns over the updates the parameters. I mean, they use an actor critic model for that. Rather, I mean, just briefly touch upon that what is interesting in an interactive data analysis session log. So the interesting part that they believe that the state in a data set, how to arrive to an interesting part, is basically just computing some of this interestingness measure, which is essentially diversity, dispersion, and peculiarity of a data of the view, and the conciseness of the view. So basically, diversity actually measures some sort of a variance. Dispersion is basically kind of measures, I mean, how similar the elements are within the data. Peculiarity actually measures whatever the view that you are looking at, it has got a reference, it has got a distribution, how it is different from reference distribution. If it is too lopsided, then we say that the view is peculiar and give a high score on that. And conciseness essentially computes the how concise the view is. Basically, the smaller the view is, the better it is. So these are some of the interestingness scores that they use, and then they try to predict using these interestingness scores that what will be interesting in the next action as the next action that they want to take, so that user can get something which is insightful. Just in the interest of time, I'll probably just finish off with this example. So I tried this out in the chat GPT, that the same table that I started with, and just wanted to see what kind of a result that I get. So the question was, what are the insights based on the following table? And it did show me some of the insights, but still I didn't see that the insight that I was searching for, right, going into the data cubes and finding out what are the major parts of the data cubes which are really interesting for the user. Those are the things it could not actually finally return. It showed some of the very boundary kind of analysis, which are like mean, median, mode, which is a significant class, and all of those analysis it showed. So in the interest of time, I probably stop here. So summary is, a lot of research is going on. The only bottleneck there is no sequential, there is no user, not much of a user data that is available, that is the recorded session, that how a user actually navigated through a data set and get to a final insight. Those kind of data are difficult to get. So that's why this reinforcement learning kind of approaches have been used, where there are some interestingness measures have been used pretty much that are created by the authors. And these are pretty much the references of my presentation. And yeah, I'll be taking questions if there is any.
Any questions from the audience? Okay, so I have one question. So in reinforcement learning technique, what is the explicit form of reward that you use?
Okay, so basically they use a weighted measurement of these. Okay, so they used a weighted measurement of all these three rewards actually. So basically they computed the like how different the data set, how the display is having different trains as compared to the overall data. And then they also looked at you are not going back to the same data set, the same portion of the data again and again. And then also the coherency. So basically there is a manual expert that is there who actually decides on what is the best action at that moment to be taken and how close it is to the action that the system is trying to take. So all these three things they scored it, and they actually then come up with a weighted version of that reward. That's what they used.
Okay, so that's from me. If you have any other questions, otherwise, yeah, thanks to the speakers for this nice tutorial. Thanks. Okay.